Well, thank you very much, Jeff, for that introduction. Today, I am Willem Schreuder, AC0KQ, and I am actually the talent today, in addition to being the director for continuing education at Rocky Mountain Ham Radio. This is our last RMHAM University for this semester. And so please start thinking about what you want to see at RMHAM University next year. We'll pick up again in October. Hopefully we'll be able to do those in person. And if there are any particular topics that you're very interested in hearing covered, or better yet, if you actually want to make a presentation as part of RMHAM University, please shoot us an email and let us know, and we'll make a plan on what we're going to cover for next semester. Also, we will continue our series of tech talks, which are basically 1 hour's presentations on a weekday evening. That would be something that we can fit you in if you have a topic that can be covered in less time than the 3-hour deep dive that we typically do here. So today's topic is mountaintop applications of single board computers. Over in my right-hand side here, Dave, WA1JHK, is hiding, but he will be presenting in a tag team fashion with me here today. But what we're going to talk about is things that you can do with single board computers, typically Raspberry Pis, on mountaintops, and applications to ham radio in general. Today's RMHAM is actually a little different than the ones that we typically have. Most of the time, we pick a topic and then really do a deep dive into one particular aspect of ham radio. Today is going to be much more of a 30,000-foot view, where we're going to talk about a lot of different things, but not really get into a lot of detail of each of those. So, to some extent, we're giving you ideas of things that you can do, or perhaps topics for other RMHAM universities. And in fact, many times there's one slide here that maps to an entire RMHAM university that we've done either in the past, or if we can volunteer somebody, we'll do again next semester. So what we're going to talk about here in terms of applications are things like site management, how we actually control devices, how we monitor our site, make sure that everything works. Since most of our sites are actually IP connected, we'll talk about things like running, using these single board computers as DNS servers or NTP servers, or using them for network monitoring or things like that. We'll talk a little bit about repeater linking, both analog and digital repeater linking, applications such as GPRS, iGates, packet use, radio messaging stations, things like that, webcams, SDRs. The limits are essentially, endless, because these little single board computers, to a large extent, does anything that a full-size computer does, but there are obviously many things to consider in these mountaintop applications. The particular thing that we need to be considered about is the reliability, right? Many of our mountaintop sites are not accessible for a significant part of the year. It's also very noisy areas, lots of RF, and the AC power may not be very reliable. So what considerations do we need to have in order to make sure that all of our hardware stays up? And Dave is primarily going to concentrate on how we actually harden these systems so that they keep on working. Obviously, things like lightning is of significant concern. We had an RMHAM University about that just a little while ago. And of course, these computers are some of the more sensitive equipment. So what do we need to do about that? We also have to deal with the fact that it's a very high density altitude in many cases, right? So heat is your enemy. You probably don't want turning fans if you can avoid it. But we need to deal with all of those kind of problems. And of course, the other extreme is also true. There are times where we have well below zero temperatures in many of these sites. And so you also have to take into consideration that at times the temperatures will be significantly lower, well below zero, and you need to make sure that everything keeps working. So, as I've mentioned, these single board computers are essentially full-fledged computers. So why would we use one of those as opposed to a real desktop or a server installation? Well, first of all, most of these single board computers run on 5 volts DC. So it's easier to have a steady power supply when we fall back to battery. They also use relatively little current. Most of the time, they run at a fraction of an amp. If we really stress them, they run maybe about an amp or so. They often don't have fans, although there may be some heat problems, so you may have to do with something like a fan in order to deal with it. And they typically don't have spinning disks. Now, of course, in the desktop environment, we can also use solid-state disks. In fact, we recommend that you use a solid-state disk. But for the most part, there are no moving parts. They're also a small form factor, so you can stick them in the back of the rack, and they don't take up a lot of room. At some sites, that's a really big deal. But actually, one of their biggest pluses is that they are infinitely expandable in terms of things that you can connect to them. So they typically have a serial connection. They often have an I2C bus or an I2C bus. They have an SPI, GPIO, and similar things. And they also have daughter boards that you can stick on top of the board to give capabilities that you otherwise wouldn't have. So they're very useful in that particular sense. But there are also some places where a full desktop or a server application actually beats the single board computer. Generally speaking, the desktop units have better performance, right? You can put a bigger CPU in them and you can get more processing power that way. The desktop units also typically have better hard drives. So you can put SATA or similar connection to them and actually have a full-fledged, highly resilient hard drive that can take beating like if you run a database application. And of course, most of the single board computers have a fixed amount of memory and a fixed CPU. You can't expand them in that sense, whereas with a desktop you can. So, both obviously have their place, but there are lots of very useful applications for single board computers. As far as the single board computers are concerned, they really come in 2 classes. What we call a microcomputer, which is something like the Raspberry Pi or the Beaglebone Black, that is actually a computer. It's a full multitasking operating system. Most of the time that's Linux, but you can actually run Windows on it, although I wouldn't know why you would. And then the rest of them are typically referred to as microcontrollers, things like the Arduino, the Raspberry Pi Pico, the Adafruit Feather, the ESP series, basically all of the things that are Internet of Things kind of computers are the ones that fall into that category. To really bring home that example, what I would like to do is walk through an application of a very specialized application of these little boards. So what I have here is an Adafruit Feather. So the feather is basically the size of a pack of gum. Here's an example of what the feather looks like. So this particular feather that I have in my hand is, just move this a little bit, is basically the feather with a LoRa radio module on it. And this particular board is very handy for 2 reasons. Number one, it's a very small form factor that is highly expandable, but it also has a port here where you can connect one of these LiPo batteries. And with that LiPo battery, you can then power this board for an extended period of time. And that, depends, of course, on the size of your battery, but it also has a 5-volt input. And with that 5-volt input, not only can you charge the battery, but you can also run the actual board. So the application that I have here has the Feather with a daughter board that consists of a latching relay. And the part that you can't see underneath is where the LoRa board is. And so I have a 70 centimeter antenna here connected to the LoRa board. And then using the GPIO pins, I can control this relay. And so the idea is that this board, using this 250 milliamp hour LiPo battery, will run for a couple of days. And of course, we can use this in a site where we have severe power constraints. So one of the problems that we face in cases like some of these foot races is we want to deploy hardware to a mountaintop site. We want it to run there for several days, but we don't have the power budget to actually do that. So what we can do is use one of these little boards, connect to it a pair of power poles, and using the power poles to actually then power the more current hungry devices. Then I have this controller board. So the controller board, as you can see here, is run off this little 500 milliamp hour LiPo battery. But I can also run it off of smaller batteries if I really needed to. It has the same Feather board underneath, and then it has a daughter board that has 3 buttons as well as a little OLED display. And what I can now go in here and do is, with my buttons, select the thing that I want to do. In this case, I want to command site 1 on. I hit the command button, and if I had this in the scene, you would have seen that now the current is turned on my mountaintop site. I can then, if I want to command it off, simply toggle through all of the different commands. So I've got 2 sites and several commands. So I want to command site 1 off. You probably heard the relay click and the power goes off. So I have a very nice, handy program environment here where I can control this mountaintop device from several miles away using this little Feather. However, think about it. This Feather is basically an Arduino compatible device. So all I can do here is run one program at a time. So if you think of it in the terms of DOS versus Windows, for example, in the DOS world, you could run one program on your DOS computer. If you wanted to run a different program, you have to shut that down and then load a new one. The same thing is true of your Arduino or Feather or other microcontroller class of board. You can run only one program, and if you want to run a different program, typically you have to reprogram the hardware to do that. So as an alternative, I have here Raspberry Pi Zero. So the Pi Zero has a daughter board, which is referred to as a bonnet. It looks kind of like the Feather board there. It has your same LoRa board and the same OLED display, but underneath here, I am actually running a full Linux operating system. So in addition to being able to apply the same controls, I have a full multitasking operating system backing me up. So if I, for example, want to put this somewhere where I can connect to this device by Wi-Fi, I can remotely access this Raspberry Pi and run another program. Or if the application is, well, I really want to have a camera also that looks at something else, I can add a camera to it. Or if I want to run a piece of network monitoring software on my Raspberry Pi, I can do all of that in parallel to actually running this board, right? And that's the big difference between using a microcontroller versus using a full Linux box to actually run all of those sites. So the other big difference here is what I'll show you is if I were to hit the reset button on this computer or this microcontroller. Whoops, sorry. Is this better? If I hit the reset button, you'll see it'll flash that screen and we're back and running within, a second or two. Because this microcontroller basically runs one program, it basically boots into that program within a few seconds. If I were to do that with the Raspberry Pi, the Pi is going to take about a minute to actually power up in order to actually, come to the programming stage or the run level where I can start running programs. So that's a disadvantage of using that Raspberry Pi. The other thing, of course, is that I can run this Feather on this 500 milliamp hour battery all day. Whereas with the Raspberry Pi, I really need a much more reliable power supply because this thing draws somewhere between 250 and 300 milliamps continuous. And so I will probably have to have something like a power brick that I can carry around to actually power it. So the long and the short of it is all of these devices have different applications. Sometimes the most appropriate thing to use is actually something like an Arduino if you have a very specialized purpose. But for the most part, these single board computers are so versatile because in addition to being able to do the task that you really wanted to perform, you can go and actually say, oh, well, while you're at it, why don't you go ahead and do this other thing for me as well? And we have the computational power to do that without any significant increase in effort. Now, of course, there are all kinds of other things that you can do with these computers. I'm not going to have the time to go through all of them, but as an example, what I have here is a little Arduino Nano in addition to a lightning detector made by SparkFun. And so what this allows me to do is right now, it just rings that buzzer whenever lightning is detected. But you can build a circuit here where you connect this device to a relay. And when lightning is detected, it powers down all of the equipment at the site that are very sensitive to a lightning strike, waits 20 or 30 minutes, however long you want to set it, and then power everything back up again, right? Because it runs on an Arduino, this is probably going to be extremely reliable. You're not going to have problems with it failing. Or if all else fails, you can always build a watchdog timer in it that you heard it beep there, basically says, hey, I just came alive, looking out for lightning. So devices like that are very useful. And what we'll talk about here in a few minutes is, well, so what are all these wires and why do they go from here to there and what do they do? So that's by means of introduction to these single board computers. Now, of course, all of them have different hardware that you can add on to the devices. I've shown you some names or some examples, but it's important to know the names of those. So when we talk about the Raspberry Pi, the daughterboard hardware is called a HAT. Strictly speaking, that stands for hardware attached on top, but it sounds to me like that's a little bit of a strained acronym. When we then apply that to the Pi Zero, it's a little hat, so it's called a bonnet. For the Beaglebone Black, we call it a cape. On the Arduino, we call it a shield. For the Adafruit Feather, it's called a feather wing. So, these are all the same things. It's basically a daughter board that you attach to the device to do various things. Another important thing to consider when you choose the device to use is how are you actually going to talk to that device. So in the case of the Raspberry Pi, it has both an Ethernet jack that you can plug into, but it also, in some of the later boards, have Wi-Fi capabilities. So you have native IP connectivity, and typically you can run SSH to it, so you can actually remotely log into it. The Beaglebone Black similarly has an Ethernet connection, although there are actually versions of the Beaglebone Black that also have Wi-Fi. The other very commonly used device is the ESP series. So the ESP series are really a series of microcontrollers, and they're part of the Internet of Things. So here's an example of an ESP that has, as you can tell, a Wi-Fi antenna in here, but it also has a few GPIO pins. And so you can use this device to control the GPIO pins, but it may also have a serial connection. This particular one does not, but some of the other versions, such as this Feather, is basically Wi-Fi in on one side and serial out on the other side. So you can actually use this microcontroller as an Ethernet to serial conversion. These ESP devices are very easily attached to daughter boards. So in this case, this board consists of an opto isolated relay. So here's your relay, there's your opto isolator, and there's your flyback diode. And you can simply connect this device to that relay and basically access this via Wi-Fi and then turn this relay on and off, right? So it's a typical Internet of Things application, but it sort of breaks the mold a little bit, right? So it's still a microcontroller, but it has more connectivity than you otherwise would expect, because it both has Ethernet on the one side, or IP basically through the Wi-Fi connection, or serial on the other side. You can also add a daughter board to, for example, the Feather that gives you the interface to an actual full Ethernet connection. And the chip there runs a little stack that gives you the ability to connect to the device. Obviously, it only receives one telnet connection at the time, but you can program it to actually do whatever you need it to do. You could also use this as a sensor package. So here's an example of a sensor that measures relative humidity and temperature. So you can spread these around your site and then connect it via one of these ESP boards to actually read the data from it. And there are lots and lots of other examples. So just to confuse the issue, the Raspberry Pi Foundation has now come out with what they call the Pi Pico, right? And this is a Pi Pico. A Pi Pico is not a Pi. It's basically Arduino, if I can use that term as describing that class of devices. It's basically a microcontroller board that you have all of the regular connection pins. This will talk only through the serial and GPIO pins that's on that particular device, and runs only one program at a time. It can't run Linux the way all of the other devices do. The key thing, though, is that in terms of making the distinction between how you can actually access those devices, generally speaking, the ones that talk IP are the more general purpose computers, the Raspberry Pi, the Beaglebone Black, whereas your Arduino class, the microcontrollers, typically you access by talking to it either via the serial port or using something like USB. And then, of course, that ESP class, there's sort of a weird kettle of fish. And then very often, those ESP boards are simply used as IP to serial connections so that you can actually access your microcontroller. Um, most of the interesting connections that we get off of our devices are actually through lower level connectivity. So obviously you can use USB, both the Raspberry Pi and the Beaglebone Black have USB ports on them, and you can talk to any other USB devices, but they also have serial connections. And so if you need to talk to another device on using a serial protocol, it actually has native support for that. One thing to remember is that it's actually TTL level serial as opposed to RS-232 level serial, but most devices actually support that. The more interesting ones is I2C, which is integrated circuit connections, or SPI, which is the serial peripheral interface. This is really a way of talking to fairly intelligent devices on the other side, and it just gives you special protocols to do this in a very fast way. Of course, GPIO, or general purpose input-output, is really what these devices are known for. Some of those pins are actually specialized. So for example, you can program them for pulse width modulation. So this allows you to basically, through rectification, give you different DC output levels, or you can turn it into sound by basically just say, twiddle this pin at a certain speed and a certain pause on-off ratio to get whatever result you want. You can get some one-wire connections, and generally those GPIO pins are very versatile because by bit banging them, in other words, controlling the up and down of those pins, you can basically talk any general purpose connection or protocol to actually make that work. Some of the devices also have analog in and out. The Raspberry Pi doesn't happen to have that natively, but that's also something that you can use to measure voltages and things like that. So just a little bit more information about each of those. So most of the serial connections are typically either USB or serial. These connections are point-to-point. For the serial connections, they are TTL level, in other words, basically 0 and 5 volts, whereas the RS-232 standard actually requires plus or minus 15 volts. So depending on the device that you connect to, you may require a level converter, typically something like a MAX 232 chip. The lines that you need to talk to that is basically receive and transmit, and then the ground. You can also optionally use RTS and CTS, basically request to send and clear to send, but those are not required to actually communicate with other devices. And speeds up to about 115,000 bits per second is commonly supported by these devices. So a very convenient way of communicating with other devices. Of course, the Universal Serial Bus, or USB, has kind of taken over from serial as the best way or most widely supported. It's a 4-wire connection, so typically ground of plus 5 volts and then the 2 data lines. And then USB-C adds a bunch of other lines that I don't exactly know what the heck they do, but there's more pins, so they do more things. The speeds can vary from about 1.5 megabits per second to, in the latest versions, 20, and I think the new version is actually 40 megabits per second. So very, very fast connections via USB. And then the other nice thing about the USB, of course, is that you can actually extend the USB using a hub. So you can actually connect to multiple devices, at least electrically, as long as you can address them. The I2C, or I2C, really, the integrated circuit way of communicating is very useful for connecting between basically chips. So for example, there's a chip called an INA219 that is a voltage and current sensor. The way that you actually read the voltages and currents off of those is that you talk to it using the I2C bus. It's a bidirectional serial bus that supports up to 127 devices. So you have your master which is typically your Raspberry Pi. And then you can have all of these devices. You just need to make sure that they have a unique address, and they are referred to as slaves. In order to talk back and forth, you really need 4 lines. So there's the ground, and typically the power, it goes with the same lines, although that's not really part of the protocol, although I think it sets the levels. But then you have a clock line and a data line. And you basically, the slave sits around and waits for the master to say, hey, tell me something, and then they send a reply back. The default speed at which that happens is about 400 kilobits per second, so about half a megabit per second. But that's actually variable. You can configure it for different uses. And the kinds of things that typically you connect to via the H2C bus is things like the INA 219 current voltage sensor that I've mentioned. Very often LCD displays that connect to your devices are controlled that way. Temperature, pressure, humidity, all kinds of sensors where it's convenient to have this parallel bus is typically connected via that bus. The other commonly used bus is called the SPI, which stands for Serial Peripheral Interface. This is also a bidirectional serial connection, but it's actually full duplex. And it can run much faster, up to about 250 megabits per second. And this is typically used to connect things like memory, or perhaps an Ethernet connector, or GPS, or something like that, where you really need to move a lot of data. The architecture, however, is quite a bit different. So what it does is that you have it's called MOSI and MISO, master out, slave in, and master in, slave out. So it's basically a 2-directional path that is connected in parallel between all of the devices. And then to select the device that you want to talk to, you've basically got a chip enable or a chip select line that you say, that slave is the one that I want to talk to, right? And so because all of the IO is in parallel or wired in parallel, everybody receives it, but unless the chip select line is high, it's not going to react to it. And when the reply comes back again, that's the same way the control is handled. The downside of this particular interface, of course, is that you need a line per each of your slaves, right? So in this particular figure, there are 3 chip select lines or chip enable lines, sometimes it's called, that selects those. So this protocol is limited a little bit in the sense that you need as many pins to actually as you have slaves that you want to connect to. Of course, the most commonly used is the general purpose IO. So the general purpose IO is bidirectional. It's basically digital. So typically it's 3.3 volts. So 0 meaning 0 and 3.3 volts being 1 or within a range. These GPIOs can have special functions such as pulse width modulation. So you can program them in the firmware as opposed to banging the lines up and down. But the main thing to remember is that not only are they 3 volts, but they are very limited in terms of the amount of current that they can supply either as a sink or as a source. Typically, it's around 50 milliamps, although you should really keep it to around 5 to 10 milliamps if you can. The key thing about these GPIO pins is that they are directly connected to the actual CPU. So they're directly controlled from the system on chip main CPU that the board has. So they're very sensitive to transients that come into that pins. And you also have to make sure that you don't draw too much current because you'll burn those up very quickly. And they're also 3.3 volts, right? So you may get away with putting 5 volts in them, but don't do it. It's not good for them. So most of the time, you're going to have at least 100K, a 1 kilo ohm resistor in series on all of those pins. Some devices actually have analog input and output. So the Raspberry Pi doesn't have analog I/O, but the Beaglebone Black does, and so does the Arduino, or at least some of them. And if you need something other than the native 1.8 volt that the Beaglebone Black supplies, you can always use a voltage divider. The Feather, for example, has an analog input on pin 7 that is a voltage divided input from its battery. So what you may have noticed when I showed you the little application for that mountaintop controller, it actually tells you what the battery voltage is. Well, you get that by simply reading pin 7, taking whatever value is there in volts and multiplying that by 2, and that tells you what the current state of your battery is. So what that particular program does is it sends you an update once a minute that says, hey, I'm now at 3.6 volts. Bad things are going to happen at 3.5 volts, so you better be prepared. The key thing with all of these pins are that you have to be really, really careful that you don't get RF into them and that you don't overload them. So let's talk about the Raspberry Pi in particular. There are quite a few different models, but the Raspberry Pi 3B Plus is my favorite. It basically has this 40-pin GPIO connector. It also has a few other pins on there, but that 40-pin connector is where you mostly connect things to. You can have a built-in display using the DSi display controller. It takes an SD memory card for running the operating system and other storage. You power it using a micro USB, a USB port. It has HDMI out if you want to actually connect a monitor to it. It has a camera connector where you can run a built-in camera. I'll talk about that a little bit more. And it has an audio or video out jack, but it's only audio out, analog audio, I should say. And it has no analog audio in. Of course, it has an Ethernet controller. It's up to about 100 megabits per second in the Pi 3. It's up to a gigabit per second on the Pi 4. And then it has 4 USB ports that you can connect to. So why the Raspberry Pi in particular? Well, first of all, it runs a full multitasking OS, basically Debian-based. And so you've got all of that infrastructure available to you. There has been millions and millions of those sold. At last count, something like 35 million. So it's being actively developed. There are new versions coming out all the time. For the most part, those new versions are backwards compatible. But the key thing is that you have a very large user community. It's by far the most popular single board computer. And so if you have a problem, chances are somebody else has already faced that problem, and you can go and Google for a solution. There's also many, many different hats that you can add to it that extends the capabilities. And I'll show you some examples of that as we go along. But all of the shortcomings about it doesn't have this, well, there's a hat for that. The cons on it is that the Raspberry Pi has only a single serial port up to version, the first version 3, and then a second serial port was later added. By comparison, the Beaglebone Black, for example, has 4 serial ports. It has no analog I/O, but you can, of course, add that to via appropriate hat. And it has no native audio input, so, or at least analog audio input, which again, also can be added as a hat. Perhaps the biggest limitation of the Raspberry Pi, though, is that it connects to essentially all peripherals via the USB hub. So what the picture in the lower right-hand corner shows is that we have the GPU that talks to the RAM and the general purpose I/O, but the Ethernet connections and all of the USB connections actually connect through that USB hub. So the speed at which you can talk to the USB hub limits everything. So in the older versions of the Raspberry Pi, even though they may have 100 megabit or a gigabit Ethernet connector, till they actually upgraded to USB 3 in the Raspberry Pi 4, the speed at which you could use those peripherals was highly limited. And as I've already mentioned, a lot of those pins connect directly to the CPU. So any wires are antennas, and in a high RF environment, that could be a death knell. So in terms of the models of the Raspberry Pis, there's actually more than what I've shown here. But basically, the Pi 3 is a quad-core 1 gigabit RAM device that has either 100 or a gigabit Ethernet connector. Even though the 3B Plus has a gigabit Ethernet capability, again, it's limited in how fast it can talk to that because of the USB bus. The Pi 4 actually upgraded that to a USB 3 device, and so its gigabit connector actually runs a gigabit. They also have built-in Wi-Fi, both 2.4 and 5 gig in the case of the Pi 4. They have 4 USB ports, and generally speaking, the price is about $35, except for the Pi 4s. If you actually buy the ones that have 4 or 8 gigabytes of RAM, the price goes up to about $75. By comparison, the Pi Zero is $5 for the original and $10 for the Zero W. The main difference being that it has Wi-Fi. The other big difference between the Pi Zero and the models 3 and 4 is that the Pi Zero is a single-threaded core. It does multitask, but if you want to run multiple programs, basically the one program has to stop running before the next program can run. So they timeshare at the millisecond scale, so you can still run the preemptive multitasking on them. But the big advantage of the Pi 3 and 4 is that they are quad-core processors. So you can actually literally have 4 programs executing simultaneously, which is very important if timing is of significant concern. So the pinout on the Pi between the Pi 2 and the Pi 3, or really the Pi 2B, the plus version of B, added the extra pins to make it a 40-pin connector. But this slide just shows that some of those pins, the GPIO pins, can be repurposed. So for example, the yellow area shows where the serial connector goes. The magenta box shows where the SPI goes. You can see where the chip enable lines go. The cyan box shows the I2C connections and so forth. So very useful for connecting to things. I just want to take a little bit of a side note here and talk about the Beaglebone Black. The Beaglebone Black has similar capabilities, but the main thing about it is that it actually has 2 rows of connectors on both sides. So instead of having 40 pins, it actually has 92 pins that you can connect to with those hats. Here's all of the pinouts. So all of the different colors again show similar assignments, but you can also repurpose a lot of these things to either be GPIO pins, so they don't have just one task. In terms of pros and cons, the nice thing about the Beaglebone Black is that because the capes mount on both sides, they're mechanically more sound. It has more serial ports. It actually has 4 simultaneous serial ports, and it also has 8 analog input pins, although they're only 1.8 volts. By repurposing them, you can have up to 67 GPIO pins, whereas on the Raspberry Pi, you've only got 26. The cons is that it's a more expensive board. It's about $80 a piece. That price has gone up significantly in the last few years. And there's also industrial versions that cost up to about $150, but are more hardened. There's a much smaller user base. They're not as popular as the Raspberry Pis, and so consequently, there's fewer capes available. It also has only a single USB connector to it, so it's limited in that sense. So all of these, of course, runs off of SD cards. Typically, the operating system requires about 4 gigabytes, I beg your pardon, for the desktop. If you run them headless, the way I typically do, the operating system takes less than 1 gigabyte. But I typically prefer the 16 gigabyte cards just because it gives you a little bit more spreading of wear on them. And it's basically more than you would ever need for most of our use. The Raspberry Pi operating system, as well as the Beaglebone operating system, is optimized to minimize the wear on the SD card. But the key thing is that it's still an SD card, right? So don't try to run a database on this. You'll wear that SD card out much sooner than you would like. The other thing is don't cheap out. Buy a reputable brand. I swear by the SanDisk Ultras, which is pictured here. But basically anything like a Samsung or any of those more well-known brands is typically the best kind of card to use. 16 gigabytes is about a good price point. If you buy them in a 3-pack, they're about $6 a piece for those. And I've had these on mountaintops for 5+ years, and I've not yet lost a single one. Actually, that's not quite true. I did lose one due to a direct lightning strike, but not only did it took out the entire Raspberry Pi, it took out half the site. So against lightning, there's not a lot you can do if it's a direct strike. The Raspberry Pi or the Beaglebone Black also does not have a real-time clock. So if it's important for you to have a real-time clock that is not reliant on an IP connection, you can buy a daughter board that basically takes a little battery, like a 1220, and that adds a real-time clock to it, which is often well integrated into the operating system. The Raspberry Pi and the Beaglebone does have some sensible logic into it that if it was connected to the internet and you shut it down gracefully, it will actually write the current time to the SD card so that when it boots up, it will start the real-time clock at that time. But obviously, if you had it offline for 2 or 3 days, the clock will start 2 or 3 days ago until you connect it back to an internet connection, and then it will set its time back to that. Adafruit and there's also something called the Pi-Face shim, which actually has gone out of production, but if you can still find an older one, are really useful. If you need to run accurate time, you can always use GPS as well. I'll talk about that in more detail. Obviously, what's critical in all of this environment is how you power it and how you shield it. So I'm not going to talk about that in detail because Dave is going to have a whole hour to talk about that. But my preference is to use one of these buck converters that typically takes a wide range in. This particular example I have on the screen takes between 8 and 50 volts in and will put out 5 volts at 3 amps into a micro USB connector. So you plug it directly into the Pi and nobody else will plug into your 5-volt bus and add transients that you don't want. They're about $15 on Amazon, and they're basically made for automotive applications. So they're already well encased and shielded and so forth. And of course, always use short fat leads because the Pi normally needs 5.1 volts. It'll give you a undervolt warning. It doesn't say main must be undervolt, but it does give you an undervolt warning if the voltage drops below 4.6 volts. It doesn't usually die at that point, but it's really annoying to have your logs filled with that.
You'll just get 1202 errors.
Yes. The maximum voltage is 5.25 volts, right? So don't try to run this much higher than that because it actually has a very narrow voltage input range. And of course, the enclosures are critical. So there's 2 important parts to that. Is you want to make sure that it's a metal enclosure so it keeps RF out, but you also want to make sure that it's well vented. So don't make it too tight. Fortunately, the half wavelength rule applies, so you can have slots in your metal. It keeps the RF out fairly well, but it lets the air through. So the last thing I'll just talk about here real briefly before turning it over to, well, we'll first have a break and then I'll turn it over to Dave, is how you get started. Well, You download the operating system, so the Raspberry Pi OS you get from raspberrypi.org. There's basically two versions. The one is a desktop version, which comes with a whole bunch of software and drives the screen and everything else. For most applications, I use what's called the light version. It basically only gives you a text interface, but I'm generally going to use that headless. So I'm going to remotely log into it. And that a particular package is only about 400 megabytes. So it doesn't take up a whole lot of room. To copy it or to install it on the Raspberry Pi, you basically burn it to the card. If you're a real Linux geek, you use DD to copy it. Just remember that with DD, you can completely destroy your entire system in a heartbeat. So know what you're doing when you're doing DD. If you're going to run the Pi headless, the current version will not enable SSH by default, right? Because if you have it connected to the internet, here's a device that anybody can log into, right? So you have to actually enable SSH by touching a file called SSH in the boot directory. So if you stick the card back into your laptop, for example, it'll typically mount, in my case, under media Willem boot. And then what I'm going to do is create a file in there called SSH, which will then enable SSH. Once you then have the Pi up and running, typically we go in there with raspi config. Raspi config is the command line configuration utility. But there's also, if you do the desktop version, a graphical version of that. And you can do things like set the host name. Please change your password so that it's not the default Raspberry Pi password. You can change the host name and things like that. For the applications that we're going to talk about here today, one of the most important ones is the interfacing options. So under interfacing options, you can enable or disable the camera, SSH, VNC, which is basically a remote graphical login. You can turn on the SPI and I2C buses, the serial bus, the one-wire connection, and you can also enable remote access to the GPIO pins, although I'm not going to talk about that today. But basically, you go in there, you say what you want, and what that will do is it will set the configuration file. So next time you boot the Pi, the kernel will enable all of those features. To then access that hardware, basically in Linux, everything is a file, right? So once you've enabled it using raspi config, you can actually access those pins directly through the /sys directory tree. Other useful ways of getting to that is CircuitPython, which is basically a series of Python libraries provided by Adafruit that gives you a modular access to a lot of the information on those pins, but also supports the devices that you can connect to it. And there's also the Pi GPIO C library, or sometimes referred to as PigPio. It's basically a C library that you can get to all of the various features. But you can actually program the pins directly by simply using the Unix paradigm that everything is a file. So for example, if I wanted to control pin 18, I want to make it an output pin and I set its value to high, what I would do is I would echo the number 18 to this particular file called sysclass GPIO export. What that will do is now create a new directory tree under GPIO 18, so that if I do echo out, so echo is just a Unix command for send the string to there, echo out to sysclass GPIO pin 18 direction, out meaning I'm going to use this as an output pin, and then I sent 1 to sysclass GPIO pin 18 value, I basically now said make pin 18 high. If I wanted to make it low, I would just echo 0. So I can control these things from the file system. If you have a program, you can just write to these files and control the pins that way, or you can use PigPio or the CircuitPython to control things alternatively. You can also read those. If I wanted to read pin 820, I would simply echo in to GPIO 20 direction and then use cat or whatever function I'm going to use to actually read them to then control those. So the echo and of the pin that you want to use and the direction you only have to do once. And after that, you just read and write the value file to then control it. So very easy to actually do that. Support for the actually controlling the pins is built right into the kernel. So the last thing that I want to talk about here is these things are at the mountaintop. How do you get to them? Well, SSH is your friend, right? SSH stands for Secure Shell. Every Linux geek is familiar with that. Basically, from the command line, you simply say SSH, the username at the host name, and you get a terminal that is basically on that device. So every command you type gets executed on that remote device. So if it's a mountaintop device, as long as you have an IP connection, you can talk to it. If in the Linux world, in the Windows world, you would typically use a program like PuTTY to achieve the same effect. I like to set mine up for passwordless access. So by simply doing an SSH keygen, you would generate a key on your host, which you can then copy to as many of those slave devices as you need to. And then when you do the SSH user at host, as long as you have the right magic key saved, it'll just log you in without having to type in your password. So it's very easy to move from one device to the other. The other thing that we can do that I'll actually illustrate a little bit later is we have this thing called DevDB. It's basically the one program to take over the world on our network. We use it to basically manage it. And as part of that, we actually use that program to manage MikroTik routers. So the MikroTik routers have a special protocol to talk back and forth. And so the thought came up, well, but now what if I wanted to control a Raspberry Pi? Well, DevDBD is a daemon that runs on the Raspberry Pi that makes it look like a MikroTik router. So you can send commands to it, you can write files to it, and so forth. So it's a way of remotely controlling things in a secure way, so it's password protected. But it basically, we didn't invent a new protocol. We just extended the MikroTik protocol to actually do that. And I'll show you some examples of how we do that to actually remotely control a Raspberry Pi on a remote site.
Very professional, Will.
Okay.
Good morning, all. I'm Dave Maciorowski. Willem gave you a good overview of single board computers and of various types and sizes. That's a good high-level view. I was going to drill down a bit and look at some of the power problems in detail, how not to blow up your Raspberry Pi or your other single board computer, and then show you some ways to manage the site so that just to stay organized. Part of it's to stay organized, part of it's to make it maintainable at a site, and we'll talk about that more. The first slide we'll talk about is the kinds of power situations that we find ourselves in. At my house, I'm not sure I get a power glitch in a year. So a pretty simple power converter is all I need in order to run Raspberry Pis at my house or any of the single board computers. But but if you go to a mountaintop, you're going to have some problems. So that's where UPSs come in. UPSs can give you the uptime you need in order to gracefully operate your server through through any power problems that you have. Doug K2AD is off frame here, but he and I were at SQUA one year when lightning hit the power pole outside. It didn't hit the radio antennas, no radio damage, but there wasn't any AC power after a brief bright flash. And that's the kind of situation you can expect when you're at a repeater site or at a mountaintop somewhere. That's even true in other situations. And certainly it's important to evaluate your specific situation. The thing about microcontrollers, as Willem pointed out, is Arduino, Feather, the ESP series of microcontrollers, and it's almost alphabet soup of the number of them that are available. They're generally tolerant about power fluctuations. That you can remove the power and they'll gracefully power back up again, and start at the beginning of their program when the power is turned back on. But microcomputers are where we need to be careful about the power source and where the quality of the power that you're used in order to make sure that you don't corrupt the storage. It's really important to be careful in those situations with the way your power is managed. So let's talk about 5-volt power a little bit. The Raspberry Pi Foundation has documented pretty well the Raspberry Pi sensitivity to power. There's a table that shows the amount of power required for each one of the boards. On the Raspberry Pi side, if you go to raspberrypi.org and look at it, there's a link there at the bottom of the slide. That link will take you to a table showing you how much current is drawn by each of their models of Raspberry Pi. We need to make sure that we have sufficient power for not only the Raspberry Pi itself, but for any USB devices that you have plugged in. Here's a power converter. This is an AC supply. Let me get my hand out of the frame. There we go. This is a 3.5 amp converter. It's got a really long cord on it, and it's got a USB micro B for that you plug right into the Raspberry Pi, and that will give you the power that your Raspberry Pi needs. If your AC, as long as your AC is good, you're going to get the power that you need for your Raspberry Pi. And I've got several of these. This particular model, these you can see at the bottom, the link on the slide is to the Amazon webpage. I've run these for several years and not had any problems with them. And the Raspberry Pis work very well. But here's an example of what can happen. Can't use my laser pointer. Do I have an electronic laser pointer, Willem?
No, unfortunately.
Okay. So take a look at the waveform that we're talking about. Is this power supply that we were just looking at plugged into a Raspberry Pi, and where the top line is the idle voltage that that was measured at the 5-volt pin on the Raspberry Pi while powered by that power supply. What I did was I triggered the scope when I unplugged the power supply from the wall, and you can see there that it's in 10 or 12 milliseconds. That's all you get when you pull when you remove the power from the Raspberry Pi. That 10 or 12 seconds is not near enough for the Raspberry Pi to clean up clean up any memory, volatile memory that it may have that it needs to save. So this is where a UPS comes in. So you can think of a 5 volt let's see if rotate it one way or the other. You can think of this is a pie juice that we have currently displayed here. Think of it as, you know, most people are familiar with a UPS that's used for, like, on your computer or your printer, that runs off AC, charges up some batteries, has an inverter that powers the 110 volts for your equipment. In this case, this UPS takes the 5 volt in from this power supply and manages a lithium battery. This happens to be about 1,800 milliamp hours, but they're available in a very wide range of capacities. What's special about this, I'm going to turn it over, is all the circuitry that is embedded in this. There's a microcontroller under there, as well as a fuel gauge and a charge controller for the lithium battery. The whole point is that this is a fully managed power source that is good for about 3 hours of uptime on a Raspberry Pi that's not too busy. Part of it depends on what USB devices you have plugged into the USB connectors. If you're going to leave a keyboard plugged in, don't make it one of the 1 amp ones with all the lights on it, right? You're certainly going to want to maybe use a wireless one, so that all you're dealing with is the dongle at the Raspberry Pi, and then the keyboard and the mouse have got their own batteries, so you don't have to be powering those off the UPS. Sorry. Yes. So this device is, see, I did not put that on the slide. I failed to do that. Doug asked what the price is on these. These run around $60, $65 with the battery, and you can plug it right in to your Raspberry Pi, and it makes a compact package that installed that way. So it'll fit in some cases, some of the low profile cases with that one. I also built up what's that thing called a fat stack. Pimeroni has a line of products called Fat Product P. What does that stand for? Pie hats. Pie hats. Yeah, they call them fats. But I've got it set up for. I've got the connectors populated so that I could put a I've got it set up so I can expand the the Raspberry Pi peripherals horizontally instead of vertically, and that gives me a much better packaging solution. It's really rough when you get stacked up too high. It's hard to find a box, but going horizontally like this, you can find a chassis to stick it in. In most radio sites, you're going to find 12-volt power supplies, lots of them, usually high current. And the radio equipment at the site is going to run off that. Now, some of that radio equipment might be backed up, but with a battery. But there are products available called a power gate that will give you that'll manage the battery for you. It'll charge the battery and also perform a nice clean switch failover to the battery to supply your control equipment. Switch to the slide, Mark, please. So power gates are available from a couple of companies. The blue one that you see here is the one from Flint Hills Radio. Guy named KI0BK is Jim manufactures these. They're good for 25 amps and they run about $85. They used to be less. I think the pandemic has kind of shut a lot of the prices up. But it's one of the attributes of this one is how low the loss is. He uses the very low loss MOSFET switches in them in order to keep the voltage drop from across to the battery and to the radio, so that you keep your 12 volts. West Mountain Radio has theirs. I know we use both of these models on various repeater sites, and they all perform very well. I've got these, the blue one, the Flint Hills Radio one, I use as a backup power for PC-based All-Star Link nodes. Plug in a battery, plug in plug in power, and it just works. Now, in order to power the Raspberry Pi and other of the single board computers, we need to get down to 5 volts. And to do that, we use a variety of 12-volt power supplies. That's right, I don't need it. The slide that we're currently showing is the converter that Willem has experience with and has used quite a bit. These have the wide voltage range, which is really, really useful. Some radio sites are powered on 12 and some on 24 volts or as high as 28 volts. So it's good to have the wide range, input range. And there's another reason for that. Some power supplies, Astron comes to mind, when there's one failure mode where their 12-volt output goes up to about 20 volts and will take out equipment. So having the wide voltage range is really a benefit. I've seen references to this Thompson. It's available on Amazon. It also has a wide range, 8 to 40 volts. And this 5-volt 10 amp one is only $10. And it has built in, you can see the list of protections: over voltage, over current, over temp, short circuit protection. It's really important to protect your equipment and use the components that will guard it from variable power as well as loss of power. But let's put the Pi back over here. So the GPIO pins that are the 40-pin connector that's along the side of the Pi, as Willem had pointed out earlier, These GPIO pins are connected directly to the ASIC, directly to the CPU chip in the center there. That's a Broadcom part, and it takes almost nothing to blow them up. You really have to guard against letting the smoke out, in this case, literally. So on the slide, I show a few examples of what not to do. For example, don't just take a long wire and hook it up to that and run 4 or 5 feet of wire to a switch. That would be bad. Remembering that that wire becomes an antenna, and if you have a lightning strike in the area, you can couple enough voltage in there to damage those 3.3 volt pins. Some of them might only have a voltage max of 3.7 volts. Some go as high as 4.2 or 4.3. That's one of the reasons for not connecting 5 volt circuitry to your 3.3 volt single board computer. And when Arduinos first came out, they were all 5 volts. And so a lot of people have 5 volt peripherals laying around that they might want to hook up. And I'll talk about that a little more here in a minute. The best practice is to use buffers. And what you want to do is you want to buffer the signals in order for the I2C bus. You want to buffer the signals for any digital inputs or digital outputs or A to D converter inputs that you need. And if you want to use 5 volt devices, you really want to use a level translator. Look at the maximum readings. I grabbed this out of a data sheet, and notice the max on this for this particular component I looked at is 3.8 volts. And so every data sheet for every semiconductor has this as the first part of the electrical specification. Scan through the data sheet, find absolute maximum ratings, and it'll tell you what that max is either by pin or by pin category. Sometimes it'll say, well, the GPIOs have this max, but the VDD pin has a different max. So just check it out. But for hooking 5 volt devices up to the 3.3 volt, the 3.3 volt pins on your single board computers, there are level translators available. Notice I provided the schematic there for what each of those is on that circuit board. So this is a SparkFun level translator. You can use them for I2C. You can use them for just digital I/O for other devices. They're bidirectional. They have a flexible voltage range. Even though I call it 3.3 volts to 5 volts, you can use them on 1.2 volt, 1.5, 1.8 volt pins just by setting the LV, that's the low voltage power, to the low voltage, the side that you want the low voltage signals to be on, and then the HV side to the single board computer. Or you can run them the other way around if you have to. There's also opto isolators. Opto isolators literally are an LED and a transistor in a package sealed in plastic. The benefit here is because light is the only thing connecting the two sides together, you can provide a good isolation of signals so that if the LED side is out in a noisy area somewhere, like a door switch on a building, you had some lightning floating around, this can help to keep that signal out of your computer so you don't blow it up. And these only cost a few bucks. I guess I didn't put it on the slide. It's one of my favorite digital output buffers. This is a 20-pin package that has 8 MOSFETs in it. It uses SPI, so it uses the SPI interface. It's available on pretty much all the single board computers. Each output, because it's a FET, you add a pull-up resistor, they're good up to about 50 volts. And when they sync, you'll get about 150 milliamps of current draw. So they're pretty hefty. They'll drive relays nicely, and they're under $2 in single quantity. I provide the Mouser link there for those. And the presentation's on the website for all these links, so that you have the links available to go and look up the parts. This is a FET that happens to be one of the ones that SparkFun sells. I mean, there's tens of thousands of different varieties, and I just picked a sampling of them. These are in a TO220 package, so when you screw these down to a heat sink, you can draw a lot of current with one of these. Notice it's about 60 volts, and this one has a max of 32 amps. So you can control some hefty things with it. A lot simpler, and one of my favorites, one of my go-to FETs is a 2N7002, and they're under $1 in tens, let's say. They're TO92s. That's the leaded package there. They're getting a little harder to find. You can still buy them. Mouser had some in stock, but the SOT23s are becoming way more popular. And yes, okay, surface mount's harder to solder, but you can buy adapter boards and you can solder them onto the adapter board, and then the adapter board is spaced 0.1 on center. So that makes it a lot easier to use those parts. And then you could have a digital relay board. The relay board is, I fooled you, Mark. The relay board is, you can get these anywhere. On Amazon, search for SaneSmart or Electronics Salon, and you can buy singles. You can buy banks of 2, 4, 8, 16, probably 12 in there too. These are rated about 30 amps DC, so they're quite good for switching loads. There's also variations of this available for using solid state relays for switching AC. So they'd be good for line level voltages. Now, if you only have a couple of AC outlets that you want to switch, you can use an outlet strip that can be controlled by the GPIO pins. Here's, it'll stop rocking. You can connect that up to a Raspberry Pi, and it will control these outlets. This is the version 2 of this outlet strip. They originally had them, all of them normally, or half of them normally on and half of them normally off. And now they've changed that so that one is always on. That's the one you plug your wall wart into. And then you have a normally on and 2 normally off. So now you can remotely control your AC devices, whatever they are. And it's nice and safe. It's all packaged, and it's very simple to wire up. So our sites don't look like, well, maybe some of them look like that, but I swiped this picture off of the web of kind of a installation that is a little hard to work on over time. It's nice that there's different color wires, but it really is just a little too unorganized. So here's a couple of pictures of the installation. Actually, it's ours down in Cheyenne Mountain. On the left is a let's see, I don't know how to show this exactly. Yeah, there we go. This is a DIN rail, and DIN rails became really popular in in industrial control systems. You put multiple rows of DIN rails in NEMA cabinets, and then you can lock the door and keep the dust out and all the rest of that. And over the years of installing equipment at repeater sites and taking my electric drill up and drilling some holes and mounting something on a panel, soldering wires on mountaintops, yeah, we're not going to do that anymore. These things just snap on. So here on the back of this one is a bracket that just snaps on to the rail, and then just have to plug the power together. And I don't need a soldering iron to do any of that. I don't need an electric drill. And there's even let's use this other camera for this one. There are terminal strips available for breaking out. For example, many repeater controllers have DB25 connectors on them. So you just run a straight through DB25 cable from your controller to the breakout board. And then all you need at the site is a screwdriver, and you can hook the wires up. And I found those to be extremely useful at repeater sites. Here's the brackets that are on the back. Turn it sideways, and there's the other variation. So those brackets are very cost effective, and you can add to pretty much any design. That's what the blue power converter I showed you before. I put one on the back, and that keeps it pretty simple in order to put the equipment, snap the equipment onto the.
Hey, Dave, we've got a question on chat.
Yeah.
It's from Chris, K0SWE. So he says, so board design is a big factor to protect against RF and EMI. Do things like metal enclosures also help?
Absolutely. Yeah, one of the things about metal enclosures is, for example, a Raspberry Pi. A Raspberry Pi, the latest ones are running at about 1.2 gigahertz. Though that isn't the crystal frequency, that's a lot lower. So there's harmonics all the way up the frequency band from the crystal frequency. And with all those, each one of those flip-flops that's wiggling in there, you can think of as a noise generator, a miniature transmitter. And we have enough broadband noise at our repeater sites. We don't need any more. So if we can keep the noise of the computers inside metal boxes, then we help overall to keep the sensitivity of our repeaters up as far as we can. And we also want to keep the RF out. For example, if you have a high power transmitter nearby, it's amazing where RF can get. Doug and I were on Cheyenne Mountain back around the first of the year, and as we drove away, we heard KBPI coming out of the repeater. It magically got into the interconnection between the receiver and the controller, and very, very low loss, but just some, there's a rectifier somewhere that's somehow getting into the baseband audio. It was actually in the audio path. It wasn't an RF thing that was going on, but with the high power transmitters, especially in a dense area like that, you got to be able to tolerate the presence of all that RF. Yeah, we were. So back to the slides. So this is one of my installations. That's West Creek, where I use a fused power pole outlet strip, and that there's one of the battery chargers and failover switches, so the power gate, and then the that next module is called a low voltage dropout, and I have one right here. And the low voltage dropout is you set with dip switches. You can set, let's see, I think I have it dropping out at around 10.5 volts. So and I put that ahead of my server. So if the power goes out, so we're not charging the battery anymore, and the power doesn't come back before the battery discharges, we want to protect the battery, but we also want to protect the electronic equipment attached to it and not run it at low voltage. So we have low voltage dropout. These are from Electronic Salon, and they're only, I think, without the cute DIN rail mount, they're only about $12, $13. So and they're available in different voltage ranges, so we can use them on 12 volts and 24 volts. And I discovered, since we're talking about these, let me put it over here. This is a power pole outlet strip, and the power pole outlet strip. Some of them can get pretty pricey. Let's see, there we go. This has got 6 on it, and $22, also from Amazon, and also made by Electronic Salon. They've got a whole line of these things. I think they must have thousands of them. Here's another outlet strip. You can put it in a DB25 path and tap off signals from it. Also not very expensive. Lots of things to organize the repeater site. Could you give me that plastic bag, right? Yes. Putting a Raspberry Pi on a DIN rail, to me, is getting a little carried away and sort of violates my rule about putting them in a metal box. But if you have a metal box and you can afford to stand them upright, there's a thing called a dinner plate. I know, I don't know who names these, but you just mount the Raspberry Pi on it and then stand it on your DIN rail, and it keeps it all safe and secure. And in fact, if you go and you look at, I think it's the Dinner Plate website, they show a row of about 8 of them. Somebody built a cluster by snapping a whole bunch in a row on a DIN rail. Here's the bracket I showed a little earlier. Winford.com, the link there at the bottom, carries an entire line of breakout boards, and in fact, this one is the one that, yeah, that one's from Winford. It's DB25N, lots of terminals, but they have all of the mounting rails and brackets, and of the various different kinds. And then I showed you the other bracket. Here's the one I have on the blue power gate, and there's the terminal strip. That one's from Electronic Salon. That's on Amazon. So I've become a fan of DIN rail at repeater sites just because I don't need a drill. I don't need screws. Oops, I dropped the nut. Now we're fishing around in the bottom of the rack looking for them. I can build the stuff at home. In fact, one more picture. For anybody that has worked in industrial control, you probably have seen these green cases. Phoenix Contact is the one that originally created it and manufactured it. And I was at a swap fest and I found a whole bunch of them for $1. So what I did was I took a piece of perf board and built my circuit on that, so I can drive to the repeater site and snap it on the rail and call it done. I noticed the prolific use of power poles everywhere. That's the other thing that it's pretty nice it makes it easier to get things done. What didn't I show? Yeah, that's good. And I was going to talk about a couple of pieces of software or software packages, I guess, that will they're good for learning more about single board computers, and they're pretty easy to program in, and they for anybody that's done an Arduino, you now know some C++, because that's really what programming in Arduino is. And the sketches, is that what they call them? Sketches that you write in an Arduino are pretty straightforward, but it's a little low level for some people, and I'm sure there are some that have shied away from it. CircuitPython is a derivative of MicroPython, and the whole idea was to have a Python interpreter that will run on a single board computer. It's got to be small and it's got to be fast. There's no compiling. Notice with an Arduino, you need a whole desktop in order to compile your application. For CircuitPython, you don't need that. They support a huge number of single board computers. I think the last number I heard was 750, but they keep adding them. Well, people keep inventing them, so they keep adding them. For example, the Raspberry Pi Pico was one of the latest ones that they added, and about half the support is there already for it. I've got a couple of links there for the CircuitPython organization, and Adafruit is a major supporter of CircuitPython. So of course it was on many of the Adafruit boards initially, and then of course it spread everywhere. Feather, I think, was where it was first. They are working on a copy for the Raspberry Pi that actually runs on Linux. So you can use the same techniques in both places. And there's a huge number of libraries. And here's in order to support all the board peripherals, so a Raspberry Pi, as Willem was highlighting, has SPI interface and I2C interface. It's an I2S interface on there. There are libraries to support all of those, and it makes the code really simple. And shown here are just a simple way to blink an LED on and off using CircuitPython. One of the cool things about CircuitPython is you plug in the USB cable to your single board computer, and when you do that, you're supplying power to the device, but it exposes a file system. And all you have to do is open a text editor to your program in the single board computer, make changes, save it, and poof, the thing starts running that program instead of the one before you had it edited. There's no compile step necessary. It's fully interpreted. So it makes it pretty simple to iterate on solutions. Another tool that's becoming more popular is called Node-RED. Node-RED was developed by IBM a really long time ago. So this has been around on all kinds of computers for quite some time, but it's only just starting to become more published and popular. I see I didn't put a link there. It should be nodered.org. Yep. And there are they call them flows, and I'll show you what that means right now. That's a flow. Over on the left, you can see each of the functions that are available that are built into the language. So I built that one in about 45 seconds. Did it take me that long? I wanted to make the line straight, so I was kind of making it pretty, and that took 40 of the seconds. But so you just drag and drop each one of the things that you want, and then you literally just wire them up and run it. That's it. Now, if you need to be able to specify like the GPIO number of the GPIO that you want to use as input, then you can type that information in to that function, so it's specific to it. And off the bottom of that first screen, that first screen is what your I'll call it an editor, where you drag and drop and wire stuff up. But these are the rest of the functions that are scrolled off the bottom of the screen that you couldn't otherwise see. And it's an event action framework. You push a button and something happens, or a timer goes off and something happens. This is a pretty fancy one that somebody put together. I think the windows at the bottom are actually from Flex Radio. And then some of in the top half of that window are gauges of various types, buttons, LEDs. You can create those kinds of dashboards with using Node-RED. So it's pretty interesting. Something that I'm going to be playing with. Here's the links. I slid them all to the end this time. So the Node-RED organization, there's also a forum specifically for using Node-RED in amateur radio. So that's a groups.io, that's a discussion list. And one of the proponents of this is Mike Walker. Mike Walker works at Flex Radio. And there is a YouTube, he did a presentation at BayCon back in February. And that's available on YouTube. So I provided the link to the YouTube video as well as the start time on the video for his part of the presentation. And he goes through a sort of a simple flow of how to build it, but also how to use it. He uses it for automating things like, one of his examples is he has a lightning detector. When the lightning detector goes off, that forces an event to occur in node red. Node red then executes one or a series of functions, and one of those functions is to open all the relays to all his antennas after powering off all the radio equipment. So, or he can, read the wind direction, and if he's not using his beam, he can rotate his antenna into the wind in order to minimize damage to the antenna. There's all kinds of cause and effect uses for it that could be done. And that's what I have.
So the last section that we wanted to do here is just go over some of the applications of these microcontrollers or microcomputers that we can use. So the first application that Dave actually alluded to is to actually use this as a relay controller. So important thing about those relays is they have to be opto isolated. Because the relay contains an electromagnet, when you power off that electromagnet, that magnetic field collapses. And as you know from Maxwell's law, it takes that magnetic energy, turns it into electric energy. And if it doesn't have anywhere to go, you can have a tremendous voltage spike, right? So typically there's a flyback diode that short circuits that current to drain it. But the best thing to do is to actually opto isolate that. So in the example that I have right here, we actually have a bank of 4 relays. And those 4 relays happen to be controlled by just pressing one of these buttons. Sorry, press the wrong button. The buttons on the Raspberry Pi. And so you'll see there's a set of indicator LEDs that tell you whether they're powered up or powered down. And I basically just output a binary number and turn on the relays on and off. But these relays can, of course, control any kind of device that you need to. I actually have a whole set of different examples here of different relays that you could use for various purposes. So if you need only one, there's a single bank relay. There's a 2-bank relay. And if you actually want to get away from something mechanical, you can actually use one of these solid state relays. Now, notice the difference between one of these, that there's actually a normally open and normally closed switch. The solid state ones basically just turn on and off, and they're quite a bit more expensive. They're about $20 or so compared to maybe $2 or $3 for one of the 4-component bank relays for the regular ones. But you get away from the mechanical aspect of those relays, contact burning and things like that. So certainly an option. If you need really high current, you can always go for one of those. Again, this is just a single pole, but you can run a lot of current, lots of voltage through those and use that as like your master switch if you want to, for example, control your entire station and make sure that when the lightning strikes, there's no power coming into the site. So how you control this, obviously, you can use your CircuitPython to control the relay. You can use the file access, as I've shown you. That's actually what I'm using on that Raspberry Pi controller that I showed you a few seconds ago. But a fairly straightforward application, and certainly something that if you want to go to 110 volts or something like that, using a relay to actually control it would be a good way of approaching the problem. The next application that is very useful is for serial control. So let's say what you want to do is control 7330 node controller, or Any other device that just has serial, well, you already have the Raspberry Pi, right? So you can actually connect directly to it. If you need RS-232 levels, here's an example of a daughter board that doesn't want to lie steady, that you can add to your Raspberry Pi. The chip on here is a Max 232, the pin right here behind the connector. That control changes the levels from 5 volts to plus or minus 15 volts if your device requires those levels. And it provides a little bit more isolation between the Broadcom chip and connecting directly to it. Of course, since you have a USB controller, you could also use something like this. That's just a USB to, in this case, DB25 connector that you can, and also has the level change. So if you want to control something that has a DB25 pin on the back, simply plug that into the USB port on your Raspberry Pi and use the Minicom program to actually connect out to it. And again, it's one of those examples of, because it's a multitasking operating system, adding this to your Raspberry Pi is perfectly fine. You don't add any significant load to it. Just as always, make sure that things are well shielded so that you don't bring a bunch of RF into your Pi that can cause problems of all kinds of other issues. Temperature measurement is actually one of our interesting applications. So this box that I've got here, you'll see its name is Thermo. The reason it's called Thermo is that it actually has a couple of one-wire connectors to it that it then reads. And I just happen to add an Adafruit screen to it that also shows the current time and then the temperature of the two sensors. So the one sensor is just right here. And if I squeeze it, you'll see it starts recording my body temperature as it starts rising. Of course, what we typically would want to do is keep track of, for example, the temperature of the heatsink on your power amplifier or something of that nature. In that case, I have connected to here a well-shielded piece of cable with the one-wire sensor at the end. This is a DS1820. It basically looks like a little transistor with 3 leads, the center lead being the data lead, and then ground and power, although you can also run it in parasitic mode where you really just need 2 wires. In this case, I'm running it with power because with power, the conversion happens a little faster between temperature and the signal. So it's advantageous for that particular use. And so in this case, that's what I'm reading here. Of course, another interesting application is you want to keep track of the temperature on your Raspberry Pi per se. So one of the features of the file system is that if you go to sys class thermal underscore zone 0, there's a file called temp. And if you actually look at the contents of that file, it's just a number. That number, in this case, 23406, is the temperature of your CPU in degrees millicentigrade, right? So just divide that by 1,000 to get centigrade or do the conversion to Fahrenheit. It gives you the temperature of the actual Raspberry Pi. If you, for example, have the Raspberry Pi in an enclosure together with a bunch of other stuff, and you're not necessarily interested in the exact temperature, what you're just watching for is that the temperature in this enclosure has become very hot, and you need to turn on the fans to actually cool this down. This is a simple built-in way that requires no additional circuitry to actually look at the CPU temperature on the Raspberry Pi, estimate that the temperature of the Pi is maybe 5 degrees centigrade higher than the environment. And when the temperature starts approaching, let's say 40 degrees, you turn on the fans because now the enclosure has become hot. So again, another application. The problem with the one-wire approach that what I'm demonstrating here, of course, is that you're connecting to GPIO pin 18. And so you're essentially adding antennas to that pin. If you want to avoid that, you can also get a USB serial connector based on the PL2303TA chip. And what this allows you to do is to run a piece of software that will use that serial converter to actually run a one-wire installation. Because you're now connecting via the serial bus, you're at least one step removed from the CPU, so you're a little bit more isolated. As long as you keep all of the wires well isolated, you can also measure the temperature that way. So all you have to do is you do apt-get install digitemp, which is the software that you need, and then you run the program digitemp DS9097 via either serial port you need to use to actually pull out the data from there. And you can have as many of these in parallel as you need so that you can measure the temperature at a number of your locations, number of different repeaters, whatever else you need to get to. So very, very convenient for that sense. Of course, one of the other things that we may want to do is while we're at the site, we want to make sure that we can actually see what the world looks like from that site. So what I've got here is an installation that runs cping. Now, in this particular instance, I'm actually using one of the little built-in screens to show on the Pi what the actual ping times are to all of the various sites. And I'm actually on the RMHAM network here, so these are actual RMHAM network sites. I can press the button to show all of the addresses. I can loop through all of the sites that I need to see what one I want to select. And then if I hit the top button, I actually get a continuous trace route to that particular site. Now, of course, in this example, I just don't have the screen real estate to really do this well. But the cping program is basically a way of pinging a series of sites that you want to measure the times to, and then either trace route to it and see the history of trace routes, which is what I have on the slide, or you can basically look at the entire network. So in this case, you can see there was a 3-second outage to Castle Peak, Sunlight, and Grand Mesa, right? So that's the western part of the RMHAM network. Something blipped between Upper Dowd and Bellyache. Actually, it was between Bellyache and Castle Peak for those 3 seconds. So we lost connectivity for about 3 seconds, and then it came back. The other thing that this is very useful for is you have a graphical display of the ping times to the various parts of your network viewed from a specific location. So the example I'm showing here is a site that's called Saddleback, and there's a Raspberry Pi there that its only purpose really is to monitor the performance of the network from that point of view. As you can see at the top, there's a multiplier based on the color. So blue means multiply by 1, green means multiply by 10, yellow by 100, and red by 1,000. And so if you see a number blue 2, that means it's 2 milliseconds was the ping time for that. If you see a green number, let's say green 2, that means 20 milliseconds. So it gives you a good pattern of what the jitter in the network is, since, if all those numbers are exactly the same, your jitter is relatively low. You have very consistent ping times. But if you see some green numbers, some yellow numbers, some blue numbers, that means that the ping times vary tremendously to that site. And many of our applications, especially things like our all-Starlink links, and P25 even more than that, is very sensitive to a change in the ping time, right? We call that jitter. So if the time it takes to reach that remote site varies a lot, it's very difficult to accommodate or accommodate the network latency. So cping is a useful way of seeing what the network looks like from that particular vantage point, see how the ping times change. It's also a good way of figuring out things like flapping routes or split routes, right? So the the traffic from here to there goes one path, the return traffic goes another path, and you see very different ping times going the one way than the other way, or you can see that suddenly there's a change in the latency, so it's now gone through a different route. It's all basically captured there. It's basically just a C program, and we're using the curses program so that you SSH into that remote site. It passes back the results, which is displayed in this semi-graphical way, but it's basically character graphics. So it requires very little bandwidth to move things back and forth. And so you can run this without overloading your network and introducing a measurement error into the actual application. So this particular example I actually use with the NetLab as just sort of a cute way of displaying it. But even without the display, you can run this headless and still achieve that same effect. The other thing that you can use a Raspberry Pi for, of course, is domain name services, or DNS. So obviously, at a lot of mountaintop sites, we are relying on a central DNS server. But what you could run into is that the network gets isolated, and then those devices don't have a way of resolving DNS. So a Raspberry Pi is a perfect application for doing that. You just do apt-get install bind, and I have a typo there. It should be bind 9, not bind 0. I was off by one key. But basically what that allows you to do is run your own DNS server. In fact, our main DNS server for the whole southern part of our network in New Mexico is just a Raspberry Pi, and it runs all of the sites in New Mexico. There's also a particular application of DNS on the Raspberry Pi that's called the Pi hole. It is essentially a masquerading DNS server, but its specific task is ad blocking, and it gives you a network-wide ad blocking. So if you run a Pi hole at your home network and you have all of your machines resolving DNS off of it, you basically get network-wide ad blocking. Where this is useful on a mountaintop site is Google is tracking you wherever you're going, and it's generating a whole bunch of other secondary DNS traffic that really isn't necessary. So when you use a Pi hole at your mountaintop site, it really works well to work across the thinner pipes that you may actually need on some of those mountaintop sites. Something that at RMHAM we typically combine with DNS is RADIUS. So RADIUS stands for Remote Authentication Dial-In User Service. So it was originally set up for BBSs that use dial-in, but we use RADIUS to actually authenticate users to all of our routers. So instead of having to configure every router with all of the legitimate users, we simply run a RADIUS server, and the MikroTik then connects to the RADIUS server for authentication. Now, the problem with that, of course, is that if the router can't talk to the RADIUS server, you can't log in, right? So what we want to have is redundancy, and Raspberry Pis are a great way of achieving that. So again, what we typically do is we combine DNS and RADIUS on the same Raspberry Pi because it actually requires very little in terms of work to actually achieve that. The RADIUS can actually be set up to use a SQL server as the database. Now, I started out by saying don't ever run a SQL server on a Raspberry Pi, except in this particular application, your database access is largely read-only. So you update the database whenever you have to add a user or something like that, but mostly your database access is read-only, and so it doesn't wear out the SD card. So it's an appropriate way of running that. Plus, it makes it very easy to distribute your logins across the entire network. We have a central DevDB server that basically just makes a TCP connection to the database, just a standard remote access to that database, updates the users, and then disconnects, and then you have a distributed database of logins. And so you can have as many of these Raspberry Pis as you need to support all of the failover that you have to all of your routers. However, always have a system-wide login that even if there's nothing connected to it, that you can still get into the router. If not, Doug will beat you silly. Now, of course, another thing that's very useful is to make sure that all of your routers run at the same time, right? So we have built into most operating systems, and Linux in particular, something called the Network Time Protocol, or NTP. What that allows you to do is to synchronize the time between all of your systems so that if you have a problem and you need to go back to the logs and figure out what happened, NTP gives you a way of making sure that all of the logs, when it says 12:33 and 15 seconds, 12:33 and 15 seconds means the same thing on all of the devices. Now, your Raspberry Pi out of the box will run an NTP server and synchronize its own time to that, but you can also then use that NTP server to provide time to all of the other devices that you need, such as your routers and things like that. However, if you are actually dealing with trying to get very accurate time, you can actually set up your Raspberry Pi to be a Stratum 0, or strictly speaking, Stratum 1 time server. So what you do in that particular instance is you connect to the Raspberry Pi this little breakout board from Adafruit. Sorry, child-proof packaging that I have to fight. Here is a breakout board for the from Adafruit, and this is the TX and RX is serial, but if you look real closely, you can probably not read it, but there's a pulse per second line. So that pulse per second line will give you at the second a transition so that you can actually time very precisely the transition that occurs. And there's a pigtail that goes with that, as well as your very common GPS satellite antenna, which you can then put in a place that has a good view of the sky. And then your Raspberry Pi can actually use the GPS signals to set its time with tremendous accuracy. If you're using the network to time, obviously, there is some compensation for the network latency, but generally speaking, we think that you can get down to a few milliseconds, maybe tens of milliseconds, if you use the network for timing. If you have to go a very long way and there's a lot of jitter, maybe it's hundreds of milliseconds of accuracy and timing. But for many purposes, that's good enough. If you ever want to get it down to the microsecond range, you can actually make your Raspberry Pi into a very accurate time server by just giving it GPS support. Now, if you get a Linux kernel, such as a Debian distribution for your desktop system, that pulse per second kernel disciplining is actually built in. However, the kernel that you get from Raspbian does not have that. So if you actually want to use it for this purpose, either you have to become a Linux geek and roll your own kernels, or since Adafruit supports their hardware very well, you can go to the Adafruit site and actually pull down a kernel that has this particular module already built in. So you do have to do a little bit of configuring in terms of the kernel config, but it's a relatively painless process to simply add to it that you are going to use that pulse per second module, and it will actually then discipline the clock in the Raspberry Pi with this pulse per second signal, and the timing on your Raspberry Pi will then be in the microsecond range. So obviously a little bit of overkill, but anything worth killing is worth overkilling. Another very interesting application for the Pi is to use it as an iGate. So I will talk about iGates a little bit later, but there's actually a great program called Direwolf. And what Direwolf allows you to do is to connect one of these RTL SDR dongles, which is just a USB port. And then, of course, the other side goes to whatever antenna you use. This is the crappy antenna that comes with it. And by then using the Direwolf software, what you can do is to control that RTL SDR to actually decode RF signals. And in this case, we're using it to listen for APRS signals. And Direwolf specifically takes those APRS signals and decodes them, and with the appropriate configuration can report your position to APRS.5, for example. So the slide specifically highlights K0VH has iGate like this out at Akron that they use for tracking balloons. And that's great if you're just on 144390 all the time, which is its default mode, as what you see there. But when we do the balloon launches, typically we want to switch that to a different frequency and use something else. So what we're demonstrating here is that we actually have a web interface that's shown in the upper right-hand box, where you can go in and say, select the frequency that you want to use. Click, when you change the selector, it restarts Direwolf with that new frequency. This particular web interface happens to be running on the server that's at my house, but it actually remotely controls the iGate at Akron. How does it do that? Well, basically, what we do is we use the DevDBD module that we've described before to do that remote control. There's a module called API, which is just a Perl module. Of course, this is all done in Perl. Real geeks use Perl. And what it does is send or make a connection to that device. And it says, I want to write a file called freak.sh. And the contents of that file is shown on the slide, right? It just writes freak equals, and then whatever the frequency is, in this case, 144.390. How that is achieved is by having a configuration file for DevDB that says, these are the 3 things that you can do on this Raspberry Pi, and only those 3 things. You can restart Direwolf, which you do by sending the MikroTik command string run restart. And what it will then do is execute as root bin system control restart Direwolf. And Direwolf is a service that runs on the machine, so it basically restarts Direwolf. If you want to have the status of Direwolf, you send the MikroTik string run status, and what it will do is it will run system control is active Direwolf, and it will return the answer, right? So what you can see up here is it says Direwolf status is active, so it's running. And the frequency that it set is, well, how did it know what the frequency was? Well, there's a line here that says, as a root, you can write the file user local bin freak.sh, which is basically this file that I've just shown you there. And if it says you can write it, obviously you can read it as well. So you can actually write that file, or you can read it and then return the value to the interface. But as a security measure, that is the only file that you can write. Right? So the problem, of course, is since you need to be able to write this as root, you don't want to give just global root access to your program. So the devdbd configuration file says, these are the files you can read. these are the commands you can run, right? So it's basically the same concept as what sudo use, right? You can say this user can do that, except in this particular case, it's when you make that MikroTik connection to the Raspberry Pi, then it will allow you to execute those commands, but only those commands, and any other commands will get bonked. The direwolf configuration file then invokes this script here, direwolf.sh. So what it does is it snarfs in frequency.sh, right? The dot frequency.sh just says, give me whatever that file does. So it sets the variable freq to 144.390 megahertz in this particular case. This is just a pause for paranoia line, right? If, for example, that file is either corrupted or unreadable or whatever, if the variable freq isn't set, I'll set it to the default APRS frequency of 144.39. And then what I'm going to do is run the RTLFM function, which is basically how you decode the RF from using FM minus F, the frequency. So it basically sets the frequency, and you pipe that to direwolf, and the configuration file for direwolf then says, okay, I'm going to report the position to APRS.phi or whatever else configuration you want to set in there. And there we have a nice remote iGate that we are controlling. And we just have a Raspberry Pi that runs this piece of software to actually do that decoding. So very, very convenient application to actually run this remotely. And of course, you can run multiple of these if you want to. Now, I would recommend that instead of buying this dongle off of Amazon for about $20, that you actually buy this one from Newelec. So it's a few dollars more. But the nice thing about this particular device, I'm sorry, thank you, which contains the exact same electronics. The nice thing about this particular version is that it's in an all-metal case. It has an SMA connector at the end. And so this is much more suitable for using at a high RF site. And it's going to cost you $3 extra to buy this from Newelec. So buy the well-insulated version of this, and you'll just be a much happier camper. Actually, I put it so that you can see the website there. Newelec.com is the site where you would get this from. Now, of course, one of the most common uses of Raspberry Pis is to actually set up all Starlink nodes. So the nice thing about all Starlink is that it is a VOA IP-based phone technology that was adapted to radio use. So what you have is obviously your Raspberry Pi that does all of the heavy lifting, but you connect to the radio using something that's called a URI, or a radio interface module. So here is the original URI, USB radio interface. It's basically a CM119 digital audio chip that takes USB in on the one side, and it puts out analog out on the other side. It has a 25-pin connector, and at that 25-pin connector, you basically have stereo audio in and out. Now, obviously, we use only one of those two channels for the most part, although the stereo is actually convenient for mixing voice with the underlying CTSS signal, so you can actually control those and separate them. There's a couple of LEDs here at the end. One is just the heartbeat LED, the other one showing power. But it's basically turns your Raspberry Pi into a way that you can link to other repeaters. And for example, the Colorado connection uses the all Starlink technology to link the whole system together, although with slightly different hardware that I'll talk about in a second. At this time, there is a whole bunch of different alternatives to this particular original piece of hardware. For example, Repeater Builder built a better mousetrap. So the actual hardware is essentially the same, but there's a few more LEDs here that shows you a little bit more about the status of the system, right? So are you getting CTSS being decoded? Is it just carrier operator squelch? Everything else, but it's basically the same concept in terms of the overall a digital USB signal for audio being turned into regular analog signal, and then the few extra lines like the PTT line, the carrier detect line, if you get it from there, or however else you get it. And there's a whole bunch of variations of this that all gives you basically the same capabilities. So this is, Dave, do you want to say a couple of words about that particular version? Sorry, I didn't warn Dave that I was going to ask him to talk about this one.
Okay, this one hot. So what you're looking at is an RA, I think that's a 40 or a 45. So Masters Communications, that's a 35. Thank you. Masters Communications makes kits of these, and depending on the number of features that are included in the particular board, the kits start at $25. So it really is easy to get started very inexpensively with these. There's also a way to go on eBay and buy the $2 ones, and there's instructions online on how to hack them. But unless you're comfortable soldering surface mount to the pins on that CM119 you see in the center there, it's easier just to buy the kit, and he'll even solder that part on for you for a few bucks. So I think he's got about 10 variations of this now that some are customized. By the way, back on the Repeater Builder one, there's variations on that too. That one happens to be the counterpart to these other two that we're looking at, similar feature sets, but Repeater Builder, it has they also have some downsized ones, like they have some that have there's one fixed audio levels. Is that the one for the Max Track?
Yes.
Yeah, so that one plugs right into almost any of the Motorola radios, Max Track, the XPRs, and because the levels are already fixed, you can they just eliminated all that circuitry from the design, and have the fixed level already appropriate for the kind of radio you're going to plug it into.
Thanks, Dave.
Mm-hmm.
So as Dave pointed out, these little boards are available from Repeater Builder. This particular version here is where you have half duplex. So you're basically just using a Max Track radio or one of those series of radios as a transmitter and receiver. This version has simply a connector to another radio. So you can basically use two mobiles as your a repeater. So this is your receiver board, that's your transmitter board, and then the USB plugs just straight into this. And that's how you get audio and PTT out to your devices. Obviously, there's also versions of this that you can plug directly into a higher end repeater and achieve the same effect. Another way that you can actually go with this is, here is a board that is a hat on a Raspberry Pi. I haven't populated this one, but basically it has the same chip there. It has your 40-pin connector, and then there's 6 lines that come out here that basically serve that same function. It's audio in, audio out, PTT, and COS, and you can actually connect it to that. But this particular board has the option to actually turn it into something close to a hotspot. So this little device here is SA818 radio module. And what you can do with that module is put the appropriate filter here for either 2 meters or 70 centimeters, put an antenna on it, and now you essentially have a hotspot, right? So instead of using your full repeater as the device, you can essentially use this as a hotspot that you can move around. However, hotspots actually has a good application at repeater sites. If you want to listen to the quality of your repeater output, or be able to provide an input to your repeater, especially if it's an area where you don't have anybody that you can call up and say, hey, is the repeater working? Perhaps putting a hotspot or a Raspberry Pi based device such as this would be a way of providing a low power on-site transmitter that has enough output that you can actually trigger your repeater or listen to the quality of the repeater sound going out. All of this. That's a good question. And there are some people to whom you should ask that question. The long and the short of it is that all of this is basically Raspberry Pi based, right? So most of your hotspots, the Zoom spot being a good example, is basically just a Raspberry Pi with a little transmitter such as this on top of it. And obviously uses different technologies for connection, but all Starlink is a great way of doing analog audio. The capabilities of your Raspberry Pi is sufficient to run probably 2 repeaters at least, perhaps more. The thing that you have to bear in mind is that what you're going to generate is an audio stream that you're going to use to connect to other repeaters typically. And those signals are on the order of about 100 kilohertz each. And so, think about just the capability of the Pi to route that over the USB bus and out to the Ethernet device, as well as running those streams over the USB to the actual individual radios. So you want to keep that manageable. Obviously, if you go to something like a Raspberry Pi 4, which has bandwidth to burn, you can do much more than that. But for the Raspberry Pi 3, which is I would generally recommend, maybe you want to limit it to about 2 repeaters. And if you have more repeaters at a site, you have to have your head examined anyway. And so basically what that allows you to do is to run the audio in and out of your repeaters to then actually run the local repeater, as well as connect repeaters to each other. The other application that is very often used is to have a variation on the repeater that is called a remote base. So the only difference between a remote base and a repeater really is that your remote base is typically half duplex, right? So you're using it to transmit and then receive. And you set it up so that it allows only one connection at a time. All Starlink actually is, as the name suggests, a star topology. You can actually link a whole bunch of repeaters together. But in this particular case, you want to allow only one user to basically come in and connect to the device. You still use your exact same RMHAM module to actually connect between your Pi and the device itself, but the software basically reconfigures itself slightly. The other thing, of course, in order to have a remote base is that you want to be able to steer the channel. So the software actually supports VHF radios such as the Kenwoods and Motorola's, that you can steer them either by using the GPIO pin. So some of the Motorola's, you can use the pins in the back to actually change the channels. Or you can actually make a serial connection to your Kenwood radio and actually talk to it over the computer access or the CAT control. What does Kenwood call their computer control? It's not called CAT. I can't remember the name now. But you can basically send commands to it to tell it to change frequency, change modes, do whatever it is that you want to change. People have also used this to actually set up remotely controlled HF stations. So for example, the software specifically supports the FT8097, the IC706, and you can use these as HF, remote controlled HF stations, which could be a mountaintop application or just a remote application either way. So the only real difference between a remote base and the repeater is just that it becomes half duplex and you have the channel steering that goes with it. But still, you're using the Raspberry Pi actually as the brains to it. MFJ also has a particular module that they tie to the that's based on a Raspberry Pi. That's basically a remote rig system. But instead of costing $200 like the competitive units, this is, I think it's about $50 or $60 to actually give you a complete remote control of your HF or VHF rig. The actual most useful way of using all Starlink is to link a whole number of repeaters together, and you can do that in either a mixer or a voter mode using this module called an RTCM. So the RTCM is basically a microcontroller that takes in your radio signals on the one side, audio in and out, the PTT and the COS line. And on the other side, you have an Ethernet port. And basically what it will do is it will take your audio as all VoIP. It will basically take that audio and chop it into 20 millisecond segments and then send it to whatever host you have. Now, your host can be a full-size desktop computer, but actually a Raspberry Pi is also a very useful application in this particular case for reasons that I'll outline here in just a second. But so the RTCM allows you to run this in two modes. If you don't time the packets very precisely, it is typically run in what's called mixer mode, where basically you have the audio streams from all of the repeaters coming in, they all get mixed together, and then they get sent back out. Now, the RTCM also has a transmit feature, right? So it will send you audio that it's hearing on the receiver, but you can also command it to transmit on that. So typically, how you would set that up is you would have one transmitter and have multiple receivers, or it will actually support simulcast as well, although it really doesn't have the very precise timing that it does. It needs to really do proper simulcast. However, if you attach a GPS to this device, and it actually has pins where you specifically attach the GPS, you can get sufficiently precise timing that you can set this up in a voting environment. So essentially what happens in the voting environment is that you have all of the audio streams coming in. It selects the one with the strongest signal, and it selects that one to retransmit. So instead of mixing all of those inputs, it will only retransmit one of them. And so, for example, the Colorado connection on Mount Thornton actually has, what is it, 5 or 6 now? 6 receivers that it's all mixing together, selecting the strongest signal, and then retransmitting that from Mount Thornton. So you can have a strong transmitter that runs high power and has a good antenna that you can reach all of the stations, but the guy on his handy-talkie can be received well by one of these remote receivers and then get selected if that's the strongest signal or the only signal that's coming into the system. So to do all of that, you need a couple of things. Number one, you need nice stable IP so that you have fairly good predictable latency between all of the different receivers, because you can buffer it a little bit, but it isn't very tolerant of changes in the latency from, let's say, a ping time of 10 milliseconds to 200 milliseconds. You know, if it's 10 plus or minus 20, that's fine. But if it has very large jumps, it's difficult to set that buffers so that it deals with that jitter fairly well. The other thing that you have to make sure is that you have a fairly good balance between all of the radios in your system. If one has a latency of 20 milliseconds and the other one has 200, then it becomes much more difficult to handle. And so in that case, it's actually better to implement this as a hub, which is what I'll talk about on the next slide. However, the idea is that all of these signals comes into a device. It decides what the output transmission signal is, either mixed or voted, and then that gets sent out back to the rest of the system. Now, if you're a site like Thornton, where we have, do we have good AC power again? Yes. After John fixed the generator, we would use a desktop computer to actually run things, because this is a fairly intensive application. However, if you are concerned about power or have other constraints, you can actually use a single board computer such as a Raspberry Pi to do this. Bear in mind the limitations of the Raspberry Pi, and if you find that a Raspberry Pi 3 doesn't do it, you can always go to the Pi 4, because the Pi 4 puts a lot of desktops to shame. The main thing that you have to be concerned with the Raspberry Pi 4 is it runs hot. And if you have low density altitude and you don't have a good heatsink on it, you will probably run into problems. Now, there are a couple of solutions to that. One is this case that's made by FLIR. And essentially what it is a nice big aluminum case. I'm trying to get the plastic top of it here now, and it's fighting me. But basically, the case itself has an indentation on it that presses down on the CPU. So the entire case now becomes a heatsink. That helps. The bad thing about this FLIR case is the bottom. It is plastic. Plastic is not isolation from RF. So there's holes in it because you really want the airflow into the system, but may not be the very best box for that particular purpose. Here is an all metal box. It again has the perforations, but it doesn't have the actual part that goes down to your CPU. So here you have to worry about ventilation. You can put a fan on it, but putting a cheap fan on this that's going to fail halfway through the winter is probably not a good idea. So really think about the energy environment that you're in before you start using a Raspberry Pi 4 on a mountaintop application. So continuing on to the hub is basically a Raspberry Pi All-Star Link node that doesn't have a radio connected to it. So what we have, for example, again, using the Colorado connection as an example, is a desktop unit. It actually happens to be a virtual machine, but that's neither here nor there. That basically takes all of these audio streams, mixes them, and sends them back out to the nodes. However, you could use a Raspberry Pi for that same particular purpose. In fact, we use Raspberry Pis for two very particular important applications. So the one is our site out at Akron. The problem with the connection out to Akron is that it runs on commercial internet. And the latency that we get over that commercial internet is all over the place. It's sometimes 50 milliseconds, sometimes it's 20 or 200 milliseconds. And it depends on who's surfing the web out in Akron. So the All-Star system, when you're actually using your RTCM and sending the signal from Akron to Thornton, deciding on the mixing there and then sending the signal all the way back is doubling your latency, right? So the more efficient way we've discovered to run it out there is to actually put a local Raspberry Pi that serves as a node. Now we're still using the RTCM as the actual thing that connects to the radio, because an important thing about All-Star is that in order to get the K2AD seal of approval, all of your repeaters have to sound the same. So you can't use one technology in one place and a different at another. It's just very difficult to make all of the levels nice and even.
Why couldn't I have used the URIX?
Because we could have, it's just harder to get the signals levels.
Now we're supporting two platforms rather than one, but they could use a URIX.
Yes, and in fact, that's what CRA does for the most part, is it not true, Dave? Yes. So the solution that we applied out at Akron was, we're still using our RTCM, but instead of sending the digital packets all the way to Thoradin and then sending it back, we actually have a Raspberry Pi out on site. The Raspberry Pi is actually powered by the Master 3 out at the site. And it basically talks from the RTCM to the on-site pipe, fraction of a millisecond time. And then what that node does is the output from that gets connected to Thoradin. And because we're now talking between all Starlink nodes, as opposed to talking from the RTCM to the node and back, it's just much more tolerant of those audio delays, and it mixes much better. So in that particular instance, the Raspberry Pi is actually on site. The solution that we implemented for Palisade, which is in Grand Junction and in Glenwood, is similar but not quite the same. We have an RTCM at Grand Junction and one at Glenwood, but the Raspberry Pi that they talk to is actually on Castle Peak, which is near Eagle. Now we still have single millisecond transit times between there and that Raspberry Pi, but generally speaking, the Western Slope has its own node, which is just a Raspberry Pi, and it's been up there for 2 years now, and we've had failures, but it wasn't the Raspberry Pi. And then that node then connects to the node at Thoradin to actually do the communications. And it sounds good, and it tolerates the additional jitter that we get if we lose one of the other 7 microwave links between Castle Peak and Thoradin. If we lost any of those and we have to fail over to VPN, that failover happens gracefully, and it tolerates the increased latency quite a lot. So again,
the simple way of saying that is it's 1 or 2 microwave high quality hops away, but then if we lose and go to internet from there back.
Right.
Yeah.
Right. And in that case, the exact installation that's up there is one of these nice little metal cases, and the power supply that I showed you when I showed you the slides on power. Basically, it has high range in, goes directly to the Raspberry Pi, and there's nothing else running 5 volts. So we've got nice clean power, and we have not had a failure so far. So as far as linking analog repeaters are concerned, this is definitely the way to go. Of course, the analog of analog is digital, right? So in that particular instance, where did I put those? Oh, right up here. The analog equivalent, or the digital equivalent of the All-Star link, is the MMDVM. So here is the MMDVM board built by Repeater Builder that allows you to connect a digital repeater that runs either D-Star or DMR or Fusion or P25 or NXDN and something called POGSEC that I have no idea what the heck it does. But the idea is that you can simply connect the digital repeater to, or it's really just the radio transmitter and receiver to this device, and it gives you the equivalent functionality. It is, in fact, the exact same technologies that you find in your DMR hotspot, right? It's basically just the repeater equivalent of that. And this board is basically the blue board that you see on top of the case is the board that the repeater builder puts out. And the bottom is just a Raspberry Pi. Again, the Raspberry Pi provides the connectivity and all of the management functions. And then the digital signals are created by that particular board. In this case, I have the connectors to connect to MaxTrack radios, but this connector here, which I screwed down so I can't get off right now, is basically what you can then connect to, any standard repeater. What you'll also notice here is that I put a label over the micro USB here that says 12 volts, because this particular device is actually powered through this connector. So you don't want to connect 5 volts to this and 12 volts from the other side, or the magic smoke may come out. But still, this kind of technology, again, relies on those Raspberry Pi boards to actually drive the whole system. The software to make all of this work is called Pi-Star. And I'm not going to talk about Pi-Star because a couple of weeks ago, Mike K0NGA gave an entire 2-hour tech talk on how to use the Pi-Star to run your hotspot. But the software that you use to configure your hotspot is the exact same software as you use to configure your repeater. So if you're interested in that, go to the RMHAM website, or you can go directly to the YouTube where Mike described how you go about actually using it. But again, an interesting application of the Raspberry Pi. In this case, there is also an additional screen that you can connect to this. In this case, this just plugs into the USB board here, into the USB port, and without having it powered up, it doesn't look like much. But it basically is the screen that displays the status of what the Pi-Star is doing. It's a DMR connection, what the call sign of the incoming is, all of the information that you also see on your hotspot. The only difference is that this is a separate board that you connect through the USB that allows you to have your transmitter or your repeater mounted in one case, and you actually have the display that shows the status in a different location, just a little bit more convenient perhaps in terms of mounting all of the hardware. But the long and short of it is, what we can do for analog, we can do in spades for digital as well. Give me a second to clean off all my junk off the table. Now, of course, another interesting application for the Raspberry Pi is to use it with packets. So there is actually a little modem board that you can attach to the Raspberry Pi as a hat that's called the TNC Pi. Originally, John Hansen in 2FT designed this board as a connector to your desktop. And then when the Raspberry Pi came out, he actually built it as a daughter board to the Raspberry Pi. And so you can obviously generate the tones on these chips here and connect it out to your radio, and then run software on the Pi to actually control this. And there are a number of options, but the one I like most is called BPQ. So BPQ is an extremely powerful piece of software that can both be used as a BBS, but that BBS has very advanced routing features in it. So for example, the National Traffic System in Colorado runs a BPQ node called K0NTS, and that node is connected to both a VHF and a UHF packet node that you can connect to most places in the Front Range. the two nodes, the one runs 1200 baud, which is the device that you're seeing right there. And I have too many things to show and tell. Oh, here it is. Or this particular board, which can also be run as a daughter board, and I could just add to the top here, is the 9600 baud version of that device. So in this case, the interesting application actually is that the green board that you see here is called a teensy. The teensy is actually a really fast PIC controller that is used to actually decode and encode those 9600 baud signals and then basically route it back out the same pins and gives you the ability to run 9600 baud, whereas the 1200 baud version basically just uses, I believe that's the Bell chip to actually generate all of the tones. But basically both these boards, when connected to a VHF radio, gives you the packet, the ability to run packet. In order to be able to run multiple of these devices, since the Raspberry Pi really just has one usable serial port, we typically resort to I2C to run this, or what we do is to use the Beaglebone Black. So in this case, this is a Beaglebone Black. You can see there's the two TNC blacks stacked on top of that, which is basically just the equivalent for the Beaglebone Black. And it gives you a very nice solid package. In this case, because you have both the headers on both sides to store this or mount this. And in this case, I decided to go hog wild and just add another daughter board that has, interesting functionality to it. So in this particular case, the board up here in the top left-hand side is an Adafruit breakout board based on the INA2119 chip that measures the input voltage from the main bus. So you can actually use this to measure the main bus voltage. And of course, it also measures the current. This takes whatever the input voltage is, somewhere between 8 and 32 volts, through a buck down converter that puts out 5 volts at 3 amps. This then gets fed into one of those Adafruit power pumps, the 1000 power pump. And in this case, again, over here, it has a connector so that you can put a LiPo battery in it so that the Beaglebone Black in this case will keep on running even if we lose DC power. There's also signals coming out of here that then gets fed down to the Beaglebone so it can do a graceful shutdown if it starts running out of power. And then just because I had room on the motherboard, I put a real-time clock here in case it loses IP connectivity. So this real-time clock is then used to set the time. And then this header here is where I can connect an I2C chip, which then can measure the temperature on all of the different devices that are connected to it. And as you can see, this used to be the BPQ node at Conifer. The reason we have 2 of those is that you can actually set one up as a packet station. So you can use it for packet access, but you can then use the other side as an iGate. So you can listen on 144.39 and then basically just rebroadcast the packet traffic. As another example, this setup here with the 2 Motorola radios and the 2 Beaglebones, we actually used during one of our events as a 2-channel or 2-band packet station. So in this case, you can tell from the labels on the front that the one was on VHF, the other one was on UHF. And so you could connect on VHF and then retransmit on UHF, or vice versa, just however else you need to connect those. So a useful, and you can see that has the real-time clock and things like that on there as well. So obviously, the BPQ node is very useful to set up because not only can you set it up as a packet station, but you can also set it up as a radio message station, basically access to the WinLink system. You can set it up with as a digipeater and various other things. The easiest way to set it up is to download the BPQ config software and just follow the menus. The last couple of applications that I want to show you here is that just as we use the All-Star link to actually take RF and then run it down to audio, you can run a remote receiver or actually a transceiver using the software-defined radio. Now, software-defined radio can either be done using that RTL dongle, or you can use the more higher end devices such as the SDR Play, which will run you somewhere about $120 or so if you get the low end ones. Or if you want the Cadillac model, Hack RF makes a very nice device, Great Scott makes something called the Hack RF that is a very high end software defined receiver that you can then use to stream down the data. Now, the thing to remember is the bandwidth that you get out of these devices are actually very large. Like, for example, you can get about 20 megahertz out of the Hack RF. These other devices are somewhere in the vicinity of 3 to 6 megahertz. So that's a lot of bandwidth to stream from your mountaintop site to wherever you're going to use it. So one thing that you may want to do is to actually decode the RF there and then just bring out the audio that you want using something either like GNU Radio or one of the other similar packages. The thing to remember with GNU Radio or any of these SDR applications are they are extremely CPU intensive because you're doing a lot of digital signal processing. So in that case, even though I told you never to use a fan, you may want to use a device like this. So this actually is both power and a fan that powers the Raspberry Pi based on a 12-volt input, and then also has a fan that will come on if the temperature is high enough. Of course, you can also get fan shims that will do that. Generally speaking here, Raspberry Pi 3 will do okay, but you really need the power of the Raspberry Pi 4 to really do this in an efficient way. Just beware that those machines are going to run very hot, and so you have to make sure that you get everything properly cooled, or you're going to end up with a bunch of melted silicon. The last example I want to show you here is that since we are running the Raspberry Pi, what did I do with my Smoke Pi? Well, can't find it right now, but this will do. In this case, notice that there's a little hole in this case where you can actually mount a webcam. So I just needed to reach a little further. Here's a nice case, again, from Adafruit that actually shows the camera that's built right into the support for the Raspberry Pi. So it has a little ribbon cable, and as an example of a third-party camera, this one has a longer focal length, greater magnification lens that you can use. And since you've got the Pi there already, you might as well use it to keep an eye on your repeater, because sometimes all you need is tell me what the lights on the front of the repeater are, right? And instead of sending somebody up there, this is a good way of actually looking at that. You can get all kinds of cool little mounts, such as this one, that will actually mount the camera, or you can build it right into the case. Or here's an example from Adafruit that you can actually enclose the camera into something a little bit more useful. The thing to bear in mind is if you're going to be streaming video, you're going to be burning bandwidth. So you may want to actually either use stills, which you can do, or just overall try to manage your bandwidth as you need to. So if you are interested in all kinds of interesting things, what else you can do with the Raspberry Pi, we've had several RMHAM universities that we've devoted the entire session to just one of these topics. So go to rmham.org/course syllabus, and you'll find lots of past talks by myself, Dave, Conga, and several others to how to do this. Adafruit is a great resource for buying parts. A local company, Spark Fun, I always want to put in a plug for, also has lots of ham porn, right? Stuff that you would just drool over as the really nice things that you can add to your Raspberry Pi. And of course, raspberrypi.org is also the source for all of those things. So I think at this point, oh, I actually have another 7 seconds. That's all I had for today. So I really appreciate your time and joining us here. And I especially wanted to say thanks to Mark and John, who's been running the RMHAM University this last few months. They've built this amazing studio, have spent hours and hours and hours setting up all of the lighting, all of the green screens, all of the hardware here, and have not only come out here to support the people that's talking. Switch over to Doug, please. No, we're, oh, there we go. But have put together all of this amazing hardware here that we've been using to run the studio, and have spent literally days and days and days out here setting this all up and making it all work. So very, very much appreciate John and Mark's efforts, and of course for the help that we've had from all of our RMHAM University presenters, as well as the Tech Talk presenters over the last year. Thank you again very much for all of your efforts and helping us put together all of these classes. We're going to call it quits here for the summer. Of course, we have all kinds of interesting things that we're going to do here at RMHAM. In addition to maintaining all of the mountaintop sites, we've got a couple of big events coming up here, like the Dirty 30. If you're interested and would like to participate with RMHAM in all of these events, please reach out. We're always looking for more smart people that can help us do all kinds of clever things. So we very much appreciate your participation in this class, as well as all of the other activities of RMHAM. Do we have any outstanding questions in the chat?
No, there's just there's some comments in the chat. So before we shut down, if people want to kind of read through those, or if we've got any final questions for Willem, feel free to come off of mute and ask them. He can hear them. If not, I think we'll call it a wrap.
There is one comment that you could have used your 6 seconds of additional time better. Well timed, well timed.
Okay, thanks everyone, and look forward to when we start these up again next fall. And I think we'll be having some tech talks, so keep an eye on the website. Thanks everyone again for joining.